Hey everyone, in this video we are going to solve the network delay time question on Leetcode. This is a very special question because in this question we'll be using the Dijkstra algorithm to solve this particular graph question. So the question says we are given a network of n nodes labeled from 1 to n, and we are also given times, and we have to return the minimum time to get to all of these nodes if you start from node k. So in this case, k is node 2, and if we have to go to all of these nodes from node 2, so to get to node 1 will take a time of 1, to get to node 3 it will take a time of 1, and to get to node 4 it will take in total a time of 2, one to reach to node 3 and another one to reach to node 4, in total 2, so output is 2. And in any case, if there are any scenarios where we cannot reach all of these nodes, so let's say there was another fourth node which was not connected to any of these nodes, in that case we'll return -1 as the result. So this is the question. Let's see how we can do it. So Dijkstra algorithm is basically BFS plus a heap or a priority queue. So what we'll be going to do, we'll run a BFS on a graph, and we'll keep adding the neighbor nodes to the heap or a minimum priority queue. So the benefit of using minimum priority queue is it will return us the node with the minimum path. So let's understand this with an example. So we'll start from node 2 because our k is 2 in this case, and we'll push it to our priority queue. So the distance, so there will be two things we'll be storing in this priority queue. One is the time, and another thing will be node. So the time taken to reach node 2 from node 2 is basically 0. So initially we'll push 0 and node will be 2. Then we'll also keep maintaining a visited array, so we don't repeatedly go to the same node again and again. So then we'll pop this first element from our priority queue, which is 0 comma 2. So, and we'll add 2 to our visited array. So 2 is added here. Then we'll run a BFS on node 2. So what are its neighbors for node 2? So for node 2, we can go to node 1 and node 3. To get to node 1, the time taken will be 1. And to get to node 3, the time taken will also be 1. So we are not visiting right away 1 and 3, we'll just add it to our priority queue. So the time will be 1 and the node will be 1. And for 3, time will be 1 and node will be 3. Next we are done with our node 2. So next we need to pop the next element from our priority queue. So which one will we pop? So since it is a minimum priority queue, it will give us the node with the minimum time. In this case, both have same time, 1 and 1. So either one is fine. Let's take 1 comma 1 in this case. So we are here. We'll add 1 to our visited array. So from 1, what are the next node we can visit? What are its neighbor? There are none. So we'll not do anything here. Next we'll go to node 1 comma 3. So we'll come to 1 comma 3. We'll add 3 to our visited array, and then we'll run a BFS on 3. So from 3, what are the nodes we can go to? So the node is 4 and the distance will be 2. How? Because to get to node 3, it requires a time of 1, and to go from 3 to 4 it requires a time of 1. So 1 plus 1 it will become 2. So we'll add time equals 2 and the neighbor node of 3, which is 4. Then we are done with 3 as well. Next we'll pop the next element from our priority queue. Only element left is 2 comma 4. So we'll pick 2 comma 4. We'll add 4 to our visited array. And what are its neighbors? There are no neighbors to it. So we'll finish our algorithm here, and till now the maximum value we have found is 2, and this will be our output. So if it is still not clear, let's understand it with one more example. So this is the another example, and in this case our k is 1. So that means we have to start from node 1 and we need to go to all of these nodes and we need to calculate what will be the minimum time taken to reach all of these nodes. So we'll start from node 1. So time taken to get to node 1 from node 1 will be 0. So we'll add 0 and node 1, and we'll add 1 to our visited array as well. Next, we'll pop 1 from our priority queue. Now we'll run BFS on node 1. So node 1 has neighbors 2 and 3. To get to node 3, we require it takes a time of 1, and to get to node 2, it takes a time of 5. So we'll add both of them to our priority queue. So it will be added as 1 comma 3 and 5 comma 2. Next, which element will pick from a priority queue? Since it's a minimum priority queue, so it will return us the one with minimum time, and in this case it is node 3. So we'll pop node 3 from our priority queue and we'll run DFS on it and we'll add it to our visited array as well. Oh, by the way, it will not be a visited array, it will be a visited set. We'll be using a set data structure for it. My bad, I keep saying it array. So we'll on 3 we'll run a BFS again. So from 3, what are the nodes we can go to? It is node 4, and the distance to get to node 4 is 1 from 3, but from node 1 it will be 2, 1 to get to node 3 and 1 to get to node 4. So we'll add 2 comma 4 next to our priority queue. Next, which one is the minimum from our priority queue? It's 2 comma 4. So we'll pop 2 comma 4 from our priority queue. Next, we get to node 4. So we'll add 4 to our visited set. Then we'll run BFS on node 4. So what are the nodes we can get to from node 4? It is node 2. And the time taken to get to this node 2 will be 3. 1 plus 1 plus 1. So in total 3. So we'll add 3 and the node 2. Next, which one is the minimum? 5 comma 2 or 3 comma 2? It's 3 comma 2. So we'll pop 3 comma 2 from our priority queue, and then we'll go to node 2 and we'll add node 2 to our visited set. Now we run BFS on node 2. We cannot go to any other node from node 2. So we'll stop our algorithm here, and we'll see that the maximum value we have found till now is 3. So 3 will be our output. You may see that 5 comma 2 is still left in our priority queue, but even if we pop it, we'll see that it is already present in our visited set, so we'll not do anything. So this 3 will be our output in this case. The time complexity for this one will be O of E log V, where E is the number of edges and V is the number of vertices, and the space complexity will be O of V, since we are storing all of these vertices in a set and in a priority queue. So this is the drawing explanation. Let's see how we can do it in code. So first let's declare our variable for graph. So it will be an adjacency list. So it will be new array with size n plus 1, and each one will have null for now. Next, let's create this adjacency list. So we'll run a for loop. So for let time of times. So first let's get the tuple or that one array from the nested array. So it will contain from node, to node, and the time taken. Next we'll check if it is not present in our adjacency list. So if graph dot from is not present in our adjacency list. So that means we need to add a new array here. So graph dot from will be equal to a new empty array. Else, if that's not the case, then we just have to push the new element with the time. So the new element 2 and the time taken t. Cool. So we have created our adjacency list. Now let's declare our minimum priority queue. So, or we can call it min heap. So it is not native to JavaScript. So if we were not on Leetcode, we would have to build our own priority queue class for it. Leetcode provides us built-in support for minimum priority queue in JavaScript from its data structure.js library, and we'll be using that. So for that, we'll write min priority queue, and we'll define the priority will be item. We'll take a function, and which one of it will be the on priority. So it will be the item at index 1, which will be our time. So we'll be storing two things, the node at index 0 and the time at index 1. Next, we'll also need a visited array. So visited set, I keep saying it array again and again. So it will be a new set. Next, we'll need a variable. It will be let min time, which will be our output that will be returning at the end. Initially, it will be 0. And for the start, we'll just push the first node, k node in our priority queue. So for pushing it, the function is enqueue, and we'll push the node 0 with the node k and the time taken as 0, because the time taken to get to node k from node k is 0. Now we'll write the code for BFS. So while min heap dot front is not equal to null, so it will keep running until our minimum heap has some value in it. Let's pop the minimum element from our min heap. So it will return us node and total time till now. To get the minimum element, we'll write min heap dot dequeue dot element. Now we'll check if it is already present in our visited set. So if visited dot has node, if it is present in our visited set already, then we'll not do anything. We'll just write continue. Cool. Next, we'll calculate the min time. So min time will be math dot max, whichever one is maximum, our previous min time or the minimum time we get from this from which we get from our priority queue element, so which is total time. Next, we need to get all the adjacent nodes or the neighbor of this node. So for that, we'll write let connected nodes equals to graph add node. We'll check if there are any connected nodes. So if not of connected nodes, that means we'll not do anything. There are no elements to add to our minimum heap. So we'll loop through all the neighbors node, let node of connected nodes. Okay, so this one will be nodes. Yeah. And we'll get the node, the two nodes. So node num and node time from our node. And then we'll add both of them to our minimum heap. So to add that, we'll write enqueue will be pushing the node the node number, which is the node itself, the neighbor node, and the time will be the total time to get to this node and the time that will be taking this node time. So we'll be adding this total time with this node time. So it will be node time plus total time. So outside this while loop, we'll check if visited dot size is not equal to n. That means we couldn't reach all of these elements or all of the nodes. That means we were not able to reach all of these nodes, and in this case we'll just return -1. Else we'll return the minimum time that we calculated. So this is the code. Let's run it. Okay, and I made so many mistakes while writing the code. So first it will be capital S. Next it will be min heap, not min head. And also we are checking if the node is available in our visited array, but we are not adding it to it. So we'll add it as well. So visited dot add node. Okay, now let's run it again. Cool, it's working. Let's submit it. Cool. So that was it for this video. Thank you for watching.